keeping it brief. Schedules, we're gonna get started, and welcome to the AstroAI lunch talk, everyone. Today it's my pleasure to introduce Sogol Sanjaripour. Sogol is a third-year grad student at UC Riverside, where she works on a number of topics regarding data science. Sogol got her bachelor's degree from Sharif University of Technology in Tehran before moving to California. And she will be visiting us this week. So if anyone's interested in touching base with her after this talk, please just reach out. She will be sitting down in the B102 office where the other students sit, in case you want to talk to her. She's going to be telling us today about galaxy surveys and how to use the supervised learning, in particular self-organizing maps, to select for active galactic nuclei. And at this point, Sogol, the floor is yours. I encourage everyone to ask questions during the talk. It's a very informal setting, so feel free to interrupt. Okay?
Thank you so much. Thank you so much. Hello, everyone. My name is Sogol. I'm so happy to have the honor to be here today. Thank you so much for having me. I'm a third-year physics PhD student at the University of California, Riverside, and so happy to present my work. Today, I want to talk about clear skies ahead. So we're going to focus on the agent selection with unsupervised learning. If you're interested, feel free to scan the QR code over there. You can get access to the first published paper of mine about this topic. So these days, thanks to the amazing ground-based and space telescopes, we're getting access to a lot of large dimensional data sets. But finding cost-effective and efficient ways to just analyze all of these large dimensional data sets is just a huge challenge for all of us. So there are different ML methods that can help us to analyze all of these data sets in cost-effective and more efficient ways to address some of important questions in astrophysics, such as selection of different agents, doing scaling relation analysis, finding different type of galaxies, and a lot of other questions. Machine learning can help us by analyzing these data sets in much efficient ways to answer these questions. One of these ideas that I cover and that I'm going to cover during the first part of my talk today is building a bridge from photometry to spectroscopy. But why? As you all know, spectroscopy is really time-consuming for us, therefore it's expensive. Why not training a model on photometric data to predict the spectroscopic data out of it? By doing this, we're going to be able to do scaling relation analysis, and we can classify different population of galaxies, including agents or any other types. So during my first work, I collaborated with IPAC Caltech in California. So we developed method together, and I was really happy to work with them. But to address these questions, I use self-organizing maps. What are self-organizing maps? If you have not heard about them before, no worries. So self-organizing maps are basically an unsupervised learning method. They are a dimensionality reduction method. In this method, you're going to have an input layer, which is basically going to be an array of data, and each array is going to be a galaxy of yours, and each array is going to have different dimensions. Any of these dimensions can be the characteristic features of your galaxies. For example, their mass, redshift, star formation rate, different photometric measurements or spectroscopic measurements. So basically, the model is going to get all of these large dimensional arrays of your galaxies, and it's going to map all of your galaxies into a two-dimensional map. Imagine you have a chessboard, and you just simply want to put your targets into different cells of your chessboard. That's what self-organizing map is going to do for you. It's a better presentation of your data visually, and it just reduces the dimensions of your data into a two-dimensional map. But why is this model useful for us? Because it preserves the topological features hidden within your pattern, within the pattern of your data. It basically maps all of the galaxies that thinks they are similar to each other into the same cell or at least into the neighboring cells. So within this model, if you get any specific classification or clumps, probably the model is finding hidden patterns that these galaxies are similar to each other. But maybe you cannot see them visually without using these models. So it's just a dimensionality reduction method, and you're gonna map your targets into a two-dimensional map. What is the training and test sample of us during the first project? So we used CANDELS photometric data as a training sample. What is CANDELS? So a lot of you may know, but CANDELS is a catalog using Hubble Space Telescope. They got photometric measurements for more than 1,000 of galaxies. We use CANDELS data set, as you can see in this histogram, as a training data set. And then we use MOSDEF, which is basically a subset of CANDELS targets as the test sample. What is interesting about MOSDEF? MOSDEF is a subset of CANDELS data set, and it's a spectroscopic catalog. So it's a survey. They obtain spectroscopic measurements for around 1,500 galaxies using KECK telescopes in Hawaii. And basically by using MOSDEF, we're gonna have a subset of data sets that we have both photometric and spectroscopic measurements for them to compare them or making a bridge between these data sets. You can see MOSDEF sample, which is the test case, mapped onto the CANDELS, which is a training data set that we have. And here you can see 3 clumps of the redshift that MOSDEF is targeting. Here I have the results of my training for the second clump of the redshift that we have. So we trained our self-organizing map on 8-dimensional photometric colors of these galaxies. These colors are optical to near-infrared colors, as you can see here. After training self-organizing map and putting your galaxies into different cells of the self-organizing map, if you have any feature of your training sample, you can just simply color code your self-organizing map by the features that you have from your training sample. Here you can find on the top, you can find the maps of all of these photometric colors that were basically the training dimensions of our targets. U-3 to H-H2. We can see the variation of these photometric colors in different regions of the self-organizing map. And these are basically the photometric colors of your training data set. And again, as I mentioned, you can color code the self-organizing map by any other features that you have from your training target. Here, I color coded self-organizing map with the stellar mass of the training targets. As you can see, the variation of the stellar mass of the targets. We have more massive targets in these regions. And then we color coded it with star formation rate of the galaxy. You can see how these two have correlations. And you can see the redshift distribution of the CANDELS on this map. So we overall used 14,000 galaxies to train our model in redshift range of 2 to 4.6, as you can see the maps. After the training, it's just time to map our test sample onto the training sum. You can basically map any kind of galaxies that you have onto the train sum if you have the same photometric colors of those galaxies as you used in the training process. So by having the same photometric colors, you can simply map any kind of target that you have onto the self-organizing map to see where it ends up in. Here you can see the circles. The purple circles are MOSDEF samples, and the X symbols are AGNs identified within MOSDEF sampling. As you can see, MOSDEF galaxies are mapped onto the more massive regions of the self-organizing map. The self-organizing map here is color-coded on the background with the median stellar mass of the targets, of the training targets. And you can simply compare the mass of your test sample to the training sample here. As you can see, they are mapped all onto the more massive regions. But self-organizing map initially didn't have any of these informations from your data set. It just understands it from the SED shape of these targets. And this selection bias is basically a known selection bias in MOSDEF sample. By design, they did spectroscopy for more massive targets, and self-organizing map is confirming this selection bias for us. So it's showing it's a useful method. As you can see, the agents here are even mapped onto the more massive regions of the sum compared to the rest of the targets. And this is another selection bias of MOSDEF sample. As you can see, our manifold learning method is finding this selection bias, and it's representing it for us. After this, it's just time to see what different agent groups, different selection methods for finding agents using MOSDEF sample, how do they look on the self-organizing map? We have different agents, X-ray, IR, different methods for selecting agents in MOSDEF sample, and each of them has a selection bias. As you can see here, these dark blue squares are showing each group of agents. As you can see here, these X-ray agents are mapped even onto the more massive regions of the sum compared to the rest of the agents, which are light blue big symbols. And this is another selection bias in MOSDEF sample confirming the literature. And we are getting the same with self-organizing map. So you can probably use this method to find another selection biases within your data set and analyzing any type of data set better. This is again the results in the redshift range of 2 to 2.6. You can see other agents, for example, IR agents, they are better distributed onto the self-organizing map. You can see they are uniformly distributed. No specific bias can be seen. But this is my favorite plot. So this is how self-organizing map is looking into your data. This is a better presentation of your data. We are presenting our data set by just showing SED shape of different galaxies within each cell of our sum. So each of these gray SEDs are the spectral energy distributions of the training galaxies, the CANDELS galaxies. In each cell, for example, this one is a cell of the self-organizing map, and these gray SEDs are basically the average shape of the SEDs within that cell, the training sample. And then the purple ones are normal star-forming MOSDEF samples, and the blue ones are agents within MOSDEF sample. This is what our manifold learning is understanding from our data set. I have represented all of the training and test sample as their SED shapes. As you can see here, how gradually SED shapes are changing from one corner of the map to the other corner, and what distribution of the spectral energy shape MOSDEF sample is covering compared to the rest of the CANDEL sample. You can see which parts and which SED shapes are having more MOSDEF samples and which of them are lacking any test sample, as you can see. So you can visually get understanding of the SED shape of your targets and the variation by using this method. And as you can see, some cells are having more noise because the thickness of these gray SEDs are showing the noise within the SEDs of your training sample. And this part is basically the part that all of this research was based on, trying to make a bridge from photometry to spectroscopy. So as you can see here, this is the self-organizing map that we had, but this time we have all of these MOSDEF samples mapped onto the sun. Some of the cells are empty because none of the MOSDEF samples end up being in that cells. And instead we color-coded the map with these spectroscopic measurements of these galaxies. We have a spectroscopic measurements of these galaxies. Why not color code self-organizing map with the spectroscopic features? As you can see, this map, you can find H alpha over H beta ratios of the MOSDEF sample. You can find log of O3 over O2 here and its variation on the map. And the same for log of O3 over H beta. On the bottom panels, you can see how these spectroscopic line ratios show.
Yeah, sorry. Is this like a two-dimensional map on the
Exactly.
sky?
Yeah.
So you have to start the images of individual
No. It's just a two-dimensional map representing our data set. So each of these cells, we have more than 10 to 20 number of galaxies, and we're just color coding this cell by the median H alpha over H beta ratios of the galaxies within that cell.
Okay, but then what really determines the location of those points in your map?
Oh, that's a good question. So it's basically our manifold learning method. We have a bunch of galaxies and we have a 50 by 50 two-dimensional map. It's just a grid. We put our galaxies into different cells of this map. That's it. That's what our method
Okay, but what is the criteria for the galaxy to be in that part versus the other part? Because, you know, that would affect the integration or the depth of the ratio.
Exactly. Take a look at this map. What decides that which galaxy is going to end up in which cell is basically the SED shape of the galaxy. So each sum cell has a specific SED shape, and based on the SED shape of the host cell, it's going to map your sample onto the cell that its SED is the most similar to the SED cell of the host cell. Okay, SED shape of the host cell. So they should be similar to each other, and that's how self-organizing map decides which sample is going to end up in which cell. And it's conserving all of these topological features within your data. Get it? So each cell here is not a specific point out in the sky. It's just a chessboard. You have a chessboard. You just simply put your targets into different cells. But neighboring targets that are ending up in the same cell are similar to each other.
Sorry for asking you a question. So you could have also alternatively arranged them in terms of galaxy morphology.
Exactly.
Because when it comes down to a city, I don't know whether you care about the amplitude, the slope, the break, and they're like, you know, basically blue versus the red. So I know that you have a very great criteria in your one, but like it seems to be a bit complicated.
Yeah, actually we train our model using these photometric colors. So these are the photometric colors that we use, and because we are just using U minus G or G minus R, we are canceling errors hidden in each filter. Yeah, that's to answer your question. That's why we're not directly using SED, we're using photometric colors instead of magnitude in each band to count for it. Thanks for mentioning. More questions? Sure.
Can you assign any meaning to the coordinate axis?
Exactly, yes. We can find the median of any cell or any parts of your self-organizing map, median of any feature that we have of the galaxies mapped onto that median. So some of the galaxies that are mapped onto some specific cells, for example, they do not have H alpha measurements, but they do have star formation rate measurements. We can find the median of star formation rate measurements within that region of the cell.
I was asking about like meaning of the axis of the self-organizing. The end, you find that the two-dimensional grid everything is now on. And the question is whether there's like a physical interpretation of what the X and Y axis is actually representing.
That's a good question. They are basically just physical locations, positions. They're just positions. Imagine you have X-axis and Y-axis. They are physical,
Some abstract coordinate system.
exactly, it's just a coordinate, X and Y coordinate. It's not representing specific regions of the sky. It's just a two-dimensional coordinate that you have. It could be X and Y axis. But what's important is neighboring cells, galaxies that are ending up in the same cell. For example, this specific region, this specific cell, it doesn't mean anything when it comes to the position. It's just mapped there. What's important for us is neighboring cells. What are the neighboring cells features that are kind of around this specific cell? By analyzing the neighboring galaxies, we can understand better the galaxies ending up in this small region of the cell. So the position itself is not important, but the neighbors are important.
So it's similar to dimensionality, reduction, whatever you're saying.
Exactly.
Non-linear population, input features, and you map this to the.
Exactly.
And in the end, you can still interpret some structure that you see clusters.
Exactly.
You're trying to.
That's it. Yeah, perfect.
So I may not actually, I may have to skip what you just mentioned, but I know that you're saying that the solar and the galaxies that are in the neighboring feature. I'm just maybe you must have mentioned and I might skip, but what do they represent? Are these all the galaxies that have same, let's say, energy, distance, fluctuation? Okay, I'm not saying it's in that applies to the entire time. Actually, it's just a definition of this question. But what do they actually represent? They are closed in which type of spectral domain? Is it distance, energy, what?
Mass, software.
Yeah. What?
That's a good question. So that's what we're looking for. We just map all of our targets onto the trained manifold, onto the learned manifold to see how are they related to each other, to find clumps and understand the pattern hidden within our data sets. Prior to that, we don't know if the galaxy is clumped into a specific region. They are similar in case of their mass or the spectroscopic measurements. But by analyzing each clump more and more, because we have data from the galaxies ending up in each clump, we can find the similarities of them. And during the second part of the talk, you will see a clump that we found and how the galaxies there are similar to each other. So you will find an answer during the rest of the talk for the question. Yeah.
If they let you get to the second part of it. Marcus, did you have?
So one thing that might be worth looking at, so the problem with interpretability of these songs is, non-uniqueness, because if you have different seeds, the previous slide, slightly different songs. And also the basis on which you build the manifold is kind of hard to interpret because essentially fluxes, right? So SEGs convolve with builder function. One of the things that I thought might be easy to do here and that might improve interpretability, but I haven't tried, is use a different basis. So for example, you could use eigenspectra, or you could use a template set. You fit that to your photometry, and then build your manifold embedding on the on linear combination of templates. And then then if you're in a certain region in your song, you can tell them, well, I mean, there is linear combination of templates that corresponds to my position in the song. And that's maybe a little bit easier to interpret than working purely on fluxes. Because then what every point here corresponds to is actually a linear combination, not linear, non-linear combination, very non-linear combination of
Very
fluxes.
Yeah, it's a good suggestion, thanks. But to get into your question a little bit deeper, what matters the most for us when we are training the machine learning model? The number of training sample is important for us, and we do not want to lose the number of our training sample. we do not have spectroscopic measurements for a lot of targets compared to the photometric measurements that we have for vast majority of the targets. So by including spectroscopic features into the training sample, into the input layer that we have, we're basically losing huge amounts of numbers of the training sample. Why is it like that? Because if your input layer is basically an array of photometric features and then, for example, 2 spectroscopic measurements, you're supposed to have these 2 spectroscopic measurements that you are including in your training process for all of the training targets. It shouldn't be empty. You need full arrays. So by including these spectroscopic measurements, you're going to lose a lot of targets because for a lot of targets, we do not have a spectroscopy. So we tried that, and because of having low number of targets for the training process, it didn't go well, and it was not representing our manifold as good as it is with the photometry colored right now. Yeah. So let's continue. And this part was the most important part of the research. As you can see on the bottom panels, you can find the mass metallicity trends by increasing the mass of the targets. H alpha over H beta line ratio is increasing here. These blue circles are coming from the predictions of our manifold learning method, and these black X marks are basically coming from observations there in individual galaxies. You can see they align with each other, and also we are getting this mass metallicity trend that is expected to exist in high redshift massive targets. As increasing mass, we're getting more H alpha over H beta. By increasing mass, we're getting smaller amounts of O3 over O2 and O3 over H beta.
So how do you use the method for prediction of a newly seen object? So suppose you get a new SED for an object, you place it on your SOM, and then it falls in a particular cell here. What spectroscopic property would you assign to that object? The one corresponding to the value in that cell, or an average of neighboring cells? Or what if it falls in a cell for which you did not have a corresponding spectral example? How do you do it?
That's a really good question. Thank you so much for asking that. So basically, let's focus on this specific cell. As you can see, this cell is color-coded. So we have a spectroscopic measurements for this cell. Where these spectroscopic measurements is coming from? They are coming from MOSDEF sample, our test sample. We are assigning the median spectroscopic measurements within this specific cell to all of the targets ending up in that cell. So because there are a lot more targets ending up in this specific cell, they are our training targets, and we do not have spectroscopic measurements for those of them. We are assigning the median spectroscopic measurements of our test sample onto all of the training galaxies in the same cell, not neighboring cell, the same cell. Okay, and as you can see, these blue circles are coming from the predictions of the sum. They are showing the mass metallicity trends that exist in the literature. So this was the first part of the talk about the first paper we published, and it is showing us how self-organizing math as a manifold learning method is working well to understand the manifold of our data set and represent existing patterns in known data sets. For the second part of the talk, I'm gonna talk about another application of this method, this time in dwarf galaxies. So before we learned about the application of the method in high mass, high redshift galaxies, but this time, seeds of giants hunting black holes in dwarfs. Why dwarf galaxies? Why black holes in dwarf galaxies? As you know, AGN in dwarf galaxies provide crucial insight into formation of supermassive black holes. Moreover, identifying agents within dwarf galaxies is really difficult because of their low mass, low luminosity, low gas phase metallicity. They're really obscure and it's challenging for us to find an agent within dwarf region. And moreover, different agent selection methods in dwarf galaxies have a little bit of overlap. So we are having troubles finding a specific population fraction of dwarf galaxies that are probably AGNs, that are hosting, that are accreting as active galaxy nuclei. So it's difficult for us to find a specific fraction of them, and we thought, why not using self-organizing map to see the manifold of our data set and see if we are getting any clumps that are probably specific regions that we're gonna have more agents in the dwarf region. Maybe self-organizing map will understand it and answer the question that we do not know. So we train our model on 7-dimensional photometric colors. As you can see the colors here, from UV to mid-IR. Then all of these color variations are shown on the trend sum. And again, color-coded sum with the stellar mass of the target, training targets, and you can see the variation of redshift on the right plot. So we have more number of targets in the training sample. They are 30,000 dwarf galaxies from NASA's Sloan Atlas catalog. This catalog is targeting nearby low-mass galaxies using SDSS survey. And the redshift of the training sample is very small. They are close to us, smaller than 0.055, and the stellar masses are smaller than 10 to the power of 9. So in this map, you can see the background, which is color-coded by the number density of the training targets in each cell. And then agents identified in dwarf galaxy regime are mapped onto the sum. You can see in each cell what fraction of the training sample exists. In the yellowish regions, we have more number of the training sample. And as you can see, our agents are mapped mostly onto the yellowish parts of the sum, which is showing the similarities of the detected agents to the training sample. Maybe there are more agents that we have not detected yet. Yes.
Like, what is the criteria for agent?
Here you can see. So we have different groups of agents identified in the dwarf regime in the NSA catalog. As you can see, the PPT agents identified using O1, S2, helium-2, variability sources, X-ray, white selection, and broadband. So there are different published papers on each of these criteria. You can read them for follow-up, but here, circles are agents, background is the stellar mass of the training targets, and these pink squares are representing agents within each group. Can you see any pattern by looking into these maps? So the first thing that I will see is BPT agents that are more mapped onto the more massive regions of the sun. The yellowish parts are more massive regions, and BPT agents are mostly concentrated into these regions. This is a known selection bias of the BPT method. It usually identifies more massive agents compared to the other type of methods. And manifold learning is understanding this selection bias in our data set. What else? We have O1, S2, helium-2 method, variability. They are uniformly distributed onto our map in different mass and also SED shapes. But you can see the clump of the broadline selection method here. Our method is understanding the similarities between these agents and it's mapping them onto neighboring cells. But here, two separated, well-separated clumps of voice selection agents. Why is it like that? Let's see voice selection map a little bit better. Look at these two regions. These two regions are darker because they are lower massive regions. And when we map agents, you can see how our voice selection targets are mapped onto the low mass regions of our map. Is this something that self-organizing map is understanding? Is this real? We decided to put all of these targets into a histogram, agents versus all other voice agents versus all other methods. And as you can see, these voice agents are populated into the regions of the lower massive histogram, as you can see, compared to the other type of agent. So this is coming from observations. This is coming from our manifold learning. It's understanding the pattern exists within our data by just knowing information about photometry colors, which is something expected. So we have, yeah.
I have a question. I don't see that so clearly. Because I see that, yes, you get them in the same places where you get low mass. But the self-organizing map is not putting all the low mass together, all these together.
Yeah. But it's like putting most of the targets onto lower massive regions, not into the more massive regions. Like it's color coding those ones selected in the Ys onto the lower massive regions. Let me show you again. So the lower massive regions are this region, and probably somewhere around here, right? When we map them, you can see most of our voice selected ones are mapped onto the more lower massive targets, into the darker regions. Can you?
Right. Is that is because of the self-organizing map, or they just happen to be low mass and they leave it the same place because they're the same?
So
Now, I don't know.
they are actually low mass. So voice selection is really low mass, but our manifold learning doesn't know anything about mass because it was not trained on the mass of the targets. It's finding out this pattern, it's mapping them onto the lower massive regions of the manifold learning map, but it doesn't have any priority information about it beforehand. So it's something that it's understanding about the pattern exists in our data. As you can see, this is observational confirmation of what we see there.
But there are also low mass galaxies that are not identified as agent, like those things. So maybe you can go to the previous slide and show us other methods can identify those regions as AGN, or they are not just AGN.
If in the specific cells you do not have any circles, then none of our agents have been ended up in those cells. Okay. Okay, and we have 83 total voice agents. 22 of them are mapped onto the right clump, 55 onto the left clump. Why are they separated? What's important about these two separated clumps? Why are not all of them mapped on together in one specific region? Why two separated clumps? So we try to go into the spectra and images of the right clump versus left clump separately to see what is the difference of these two galaxies that our manifold learning is understanding and we didn't know. As you can see, spectra of the galaxies onto the left clump are shown here, and also the images from SPSS survey, and you can see the left on the left side. For the right clump, as you can see, we are getting more bluer galaxies, and spectrals are dominated by strong emission line characteristics of young star-forming galaxies, as you can see the peaks. But on the left clump, we are getting redder galaxy images spectra lack strong star-forming emission lines, and some exhibit broad H beta profile and blue shifted O3, which is indicative of AGN activity. There is a known contamination problem in the Weiss selection, specifically in the dwarf regime. When Weiss is selecting dwarf AGNs, it's just having difficulties distinguishing between dwarf AGNs and starburst galaxies. Because starburst galaxies in the low mass regime, sometimes they are false positives. They mimic AGN activities, but they are not AGNs. And because of that this method is selecting starburst in low regime as AGNs. This is a known contamination problem. And self-organizing map is just distinguishing between two types of galaxies in this selection. It's just selecting right clump as the probably more starbursty galaxies, and the left clump is more AGN-like galaxies, and it's finding out this pattern within our data. So based on this, we submitted a proposal for the KECK telescopes using NIRIS instrument to get measurements of some of the galaxies into the left clump in a hope to find more AGNs in the dwarf regime and study them better. So this method is giving us some information about probable AGNs that exist, and we cannot see any AGN activity in them. We should probably focus on them more to get more information about them. It's just giving us some candidates. And without using this manifold learning, it was really difficult to find out which galaxies are probably AGNs that we do not know. So we tested this hypothesis a little bit more with the observational data set that we had. We mapped galaxies on ending up into the left clump and right clump, all of them, including the training galaxies, onto the color mass diagram. And as you can see, they really separate from each other, which is again confirming the pattern we saw using our manifold learning method. For the future work, yeah.
What for some is intrinsically doing is has some activity function, so essentially puts things together that have similar photometry. So here's the statements that you've been doing previously is, blue galaxies have similar photometry to other blue galaxies, and has similar photometry to red galaxies, because red galaxies tend to be redder. But did you tweak the proximity function towards what you're really interested in? So, for example, did you have a look at modifying that a little bit? So, for example, that the song has much higher value on certain emission lines or stuff like that.
Yeah. You can do that. You can, when you're training your song, you can put the specific weight vectors for specific, exactly, for specific dimensions of your training array. I didn't put any prior information. It's an unsupervised learning method. I didn't use any prior information to weigh some colors or photometric features more than the other. So they are all equal to each other in my training. Thanks for asking. Yeah. So for next work, looking for expand these applications of AI in astronomy by using diffusion model or transformer-based models to study AGNs selected using Euclid telescope. Q1 data is out, and we're looking for find the pattern and selection biases within AGN sampled in Q1 data in collaboration with IPAC Caltech. I'm so excited for that. And here are the conclusions. You can scan the QR code to get access to the published papers about this topic. And thank you so much for being here and listening to my talk.
Very nice talk. All right. Questions, comments, suggestions? Rafa.
Very nice. Well,
How do you determine the dimensionality of the solid?
Yeah.
The number of
Cells.
cells.
Oh, that's a really good question. So finding a specific size for training the sum is really something important for us. You can use any X and Y like number for training your sum. I decided to train our self-organizing map on a 50 by 50 map. Why did I choose 50 for the size of the manifold learning map? Because it relates to the number of data set that you have in the training process. And there is a quantization error when you're training your model, and you want this quantization error to be low. What does this quantization error say exactly? It's about the similarities of the galaxies ending up in each cell. It's like a standard deviation method. It's giving you a sense of how similar galaxies ending up in one cell are to each other. So we want the quantization error to be small, as low as possible, and also the map to represent the structure of our data set. Based on that, and also the number of the galaxies that we have for the training process, we chose 50 by 50. And for finding the best quantization error value, we just did quick search. It's just simple code that you can find best size of your map to minimize this quantization error. Yeah.
Sophia, I'm gonna leave.
Yeah, so great talk. So you say that you compare the like training testing data, I think you said like CANDELS and KECK, and then you say that you can reflect selection by CGS, right? Because the MOSDEF galaxies go into like areas of hyperspace that are the entire mass galaxies. My question is, so you're creating this on your training song based on real data, and so probably CANDELS also has selection bias data that we don't know. And so do you have any thoughts on that? Like maybe there are areas in parameter space that you're not even getting because you're using real data that has selection biases already built in. Does that make sense?
Yeah, it all makes sense. So we use fraction of the data that doesn't have selection bias when we are training our map. So we are not targeting for a specific region of the sky or specific features within our training sample. We try to minimize these biases in the CANDELS sample. That's why we didn't use all of the CANDELS sample. We try to delete these biases in our sample.
But does it inherently have?
For example, by choosing a specific redshift range, you can kind of delete this redshift bias because there is redshift bias in the test sample that we have.
What about other biases?
So based on the other papers published on the CANDELS and also MOSDEF sample, we try to minimize the known biases, but there might be other biases that we do not know. And self-organizing map is understanding.
Because what I think it might be interesting, like, your talk about this, is if you train this on based on the simulation data, very
Exactly. Probably by setting different weights onto the training dimension, you can kind of deal with that problem. Yeah, it's something that just comes to my mind right now. As you suggested.
Thanks. You had one, and then you, and then we have to close. Yes.
Sure. So, well, the fact is that alien, passing into the song and getting the map that you showed. I mean, it's just a question out of curiosity. The map that you actually showed, because you were clumping, aliens that are similar in one particular comp or stock, but do you really think that it was actually the mass that made them come closer, or it could have been a luminosity, could have been any other factor? But it's just it's unsupervised training anyways. So how are we so sure that it's actually the mass of those agents that are making them close? And then you kind of like proceed to based on the wise agents, but it could be luminosity. I'm just saying. It doesn't have to be mass. So.
Exactly. I didn't say it's just mass that is the only reason made them clump there. It could be W1 minus W2 color, the feature that we use in the training. It could be photometric measurements in different bands, but it could be mass because we know SCD is related to the mass. Right?
It could be mass.
It could be mass. It's just one suggestion. It could be something else because manifold learning is understanding everything at the same time. It's looking into your data by comparing all of these photometric measurements at the same time. None of us can do this. So it could be something else. It could be a relation between this photometric feature and the other photometric feature. But we're just saying that maybe mass something.
Yeah, because what I was more concerned about that, whatever map that you're showing, is there any physical interpretation to the map itself? If we can draw, because if we know that, okay, for certain, let's say if it's math, well, yeah, then we can know, okay, if it's math, then the other galaxies that are also going through the same sun and coming up on top of that graph may have some interpretation with regards to how the math works in those regions, and you know.
It's
But if it's luminosity, then it's a different story altogether, but if it's something else, neither mass nor luminosity. So that's why I was more concerned about, is there any, like a physical interpretation to what the map has to offer?
So as I mentioned, it's just X and Y axis positions. Yeah. What's important is the neighboring cells and the clumps general feature that you can see. But you can color code your map by any physical measurements that you have. Mass, star formation rate, different photometric measurements, or even a spectroscopic measurements. But you can do this after building your manifold.
That's a
map.
representation.
That's a presentation. Yeah.
All right, let's move on so that we can.
Yeah, just.
I have one question.
Can we do the one online? Yeah, go ahead.
Hi, so I was just wondering what kind of statistical models have been used to determine and examine the influence of agents in galactic evolution.
You mean you're asking about a statistical model behind self-organizing map, or like just a selection of the agent?
So just wondering on how the influence of agent contributes to galactic evolution. So what kind of statistical models have been used to explain how agents have been helping in terms of galactic evolution?
Oh, you're asking about the role of agent in dwarf galaxies to understand different things about the other supermassive black holes? Is it your question?
Necessarily, yes. So what kind of models have been used to showcase those?
So yeah, there are some published papers. You can look for them, specifically Baldassar-Walewski 2014 paper. They are showing how these dwarf agents are related and they come together, generate more massive, supermassive black holes. So basically this dwarf region is really important for us. As we understand their formation, there are young agents, most of the time we can get information about them as they evolve and get into supermassive black holes. Sometimes these dwarf galaxies combine together, make greater galaxies, larger galaxies, and then supermassive black holes. But we want to know the seeds of these supermassive black holes, which are agents in dwarf regions. But we cannot, to answer your question better, we cannot find black holes in dwarf regime because they are too small. And given the astronomical technology that we have these days, it's really hard to find black holes in dwarf regime, unless they are accreting gas and outflows as agents. So the only way to understand black holes in dwarf regime is to study agents because of the instrumental technique that we have these days. They're too faint, too small, low luminosity. We cannot find out anything about black holes in them, unless they are accreting gas and outflow as agents. That's why we're looking for agents.
Oh, okay.
Thanks.
Quick.
Thank you.
Thank you.
Yeah, just very quick, so when I'm down on the question about the selection function, so I mean, it's modeling selection function is incredibly hard, as you know. One thing that might be useful is so currently the sum is trained on the understanding of noise and photometry, right? But if you want to compare the simulations or want to put it into another survey, it would be good to have that somewhat built with respect to noise photometry that's surface specific and you know leads to the misclassification of noise just because of the photometry, but build the sum in latent space, so unfolding stuff. And that would be generally useful because we get a lot of benefits. So first of all, it's easier to compare against simulations that don't have, where it's sometimes difficult to forward model noise, right? If that's, might be more convenient this way, but also you can put it into another survey. So you can train a sum, it's a combination of multiple different surveys, each having different noise processes, including this noise process, constrain your sum. Again, I'm not a big fan of the sum because it's kind of built on a very unphysical basis. But let's fix the sum. I don't really care about which method. But then you can essentially build like a low-dimensional representation, really of spectral energy distributions of multiple different surveys, and the position in this compressed space would then really correspond to that true photometry. I think that would be generally useful, and that might be something to work on. I'm pretty excited about this when I hear some thoughts. Probably for your specific purpose, not super immediate, but could be a nice future one.
Thank you so much. Yeah, actually, I will look into possibilities.
And then finally, Razi, quick, please.
Yeah, so yeah, wonderful. About the X-ray, which data set did you use? I'm very surprised that you have that many X-ray data actually.
The X-ray agent selected in the MOSDEF sample. So I refer you to Azadi SL 2015 paper.
No, I'm just like talking which observatory for X-ray did you use that have all of them?
It's KECK telescope. So it's MOSDEF sample, it's KECK MOSFire, I guess.
What X-ray data?
Yeah.
What where the X-ray data came?
Maybe Chandra?
I thought Chandra doesn't have that many because most recently I was looking at SPSS and a lot of them are just like missing. Maybe I'm missing and maybe we can discuss further, but yeah, it would be nice to know what is the how you solve the ion size.
So most of these are in the MOSDEF catalogs that they have identified X-ray agents. So
I see.
it's like it's all about the KECK telescope. It should be.
Okay,
Yeah, because it's all direct in the MOSDEF paper catalog.
Yeah.
It's all there, all the targets. We found them from there. Yeah.
All right, so 1 minute to the hour, so let's leave it at that. Thank you so much.
Thank you.
For those here for the rest of the week until Thursday, so let me know if you want to start.